In this BocaPhysics video, you'll see simulations of the electric field due to a variety of configurations of point charges. By investigating configurations more complicated than those usually encountered in general physics, you can get insight into the behavior of charged conductors. In the first simulation, we see the electric field lines due to a single isolated charge. In this simulation and all that follow, the electric field lines were calculated computationally. When students are instructed about sketching field lines, they are told that the field lines radiate outwards from positive charges and that they terminate on negative charges. Also, electric field lines can never cross. In the case of a positive charge, we would imagine the charge to be a source, and in the case of a negative charge, we would imagine it to be a sink. The following simulation shows the field lines in 3 dimensions. In the third simulation, we see the electric field lines due to a positive charge and a negative charge of the same magnitude. Let's assume that the charge on the left is positive and that the one on the right is negative. In the region of space close to the positive charge, the effect of the negative charge on the electric field lines appears to be minimal. The field lines radiate outwards very much the same way they do as for an isolated positive charge. Further away, you notice how the field lines are bent and ultimately terminating on the negative charge. The only field lines that don't curve are the ones that originate or terminate along the axis on which the 2 charges lie. In the fourth simulation, we see the electric field lines due to 2 charges of the same magnitude and the same sign. We'll assume they're both positive. The effect of 2 like charges in close proximity on the field lines is that the field lines get pushed away from each other. Remember, electric field lines originate on both these charges and they cannot cross. The electric field along the midplane between these charges vanishes. In the fifth simulation, we see the electric field lines due to 3 like charges of the same magnitude in a row. Notice especially the field lines originating on the center charge and how above the axis of charge the field lines are pushed so that they're more vertical. We see the same effect below the axis. The field lines get bunched up, but they do not cross. Next, we see the field lines plotted due to a row of positive charges of the same magnitude. For clarity, only 2 field lines are drawn from each charge, except for the end charges, and 3 are drawn from those. Notice that the field lines emanating from charges in the center are very nearly vertical, whereas the field lines emanating from charges close to the end are noticeably bent towards the axis on which this row of charges lies. From this simulation, we can begin to understand the behavior of the electric field due to an infinite line charge. The concept of an infinite line charge is useful when end effects can be ignored. Hence, the electric field will radiate outwards from the axis of the line charge. Every electric field line will be perpendicular to the charge and will be straight. In the seventh simulation, we see the electric field lines plotted due to a group of charges arranged to lie in a circle. An indication of the magnitude of the electric field is given by color. Brighter pink represents greater magnitude, and violet represents smaller magnitude. Notice that the electric field lines radiate outwards from the ring, and there's a bunching of electric field lines due to 2 neighboring charges. In the inside, the electric field is smaller in the center region, and it vanishes at the center. In this case, the electric field lines terminate at the center of the ring and not on a charge. In topology, this is a so-called critical point. In the 8th simulation, we add an additional positive charge that lies outside the ring. Once again, an indication of the magnitude of the electric field is given by color. Brighter pink representing greater magnitude and violet representing smaller magnitude. Notice how the presence of the additional positive charge distorts the field. The field lines still radiate outwards from the ring, but in the vicinity of the additional charge, there is a bunching of field lines. Distortion of field lines inside the ring is far less pronounced, but do notice that the center has been displaced to the right. We can begin to understand how conductors shield their interiors from external electric fields. In the ninth simulation, we see the field lines due to a sheet of charges. The field lines emanating from the charges in the center are more nearly vertical. And there's greater bending of the field lines that emanate from charges that lie on the edges. From this simulation, we can begin to understand the behavior of the electric field due to an infinite charge sheet. The electric field will be everywhere normal to the sheet, pointing up above the sheet and pointing down below the sheet. From symmetry, it is apparent that the electric field will have the same magnitude at all points equidistant from the sheet. What is not immediately apparent is that the electric field has the same magnitude everywhere above the sheet and everywhere below it. In the final simulation, we see the electric field lines plotted due to two plates. The upper charges are positive charges, and the lower charges are negative. Only field lines emanating from the positive charges are drawn. In between the sheets, the field lines are very close to vertical. From this simulation, we can begin to understand the behavior of infinite parallel plate capacitors. That is, the electric field is uniform between the plates, pointing straight down from the positive plate to the negative plate and having everywhere the same value. For finite-side parallel plate capacitors, we see that there will be fringing near the edges. Fringing is a consequence of the conservative nature of the electric field. That is, the curl of the electric field vanishes in electrostatics.